Well, hello, this is Ms. Dagenford, and we're going to be looking at the types of graphs that we're going to be using this year in AP Biology. First, we want to look at the reason why we graph. Now, you've heard us in previous classes talk about this. We want to see the trends in our data. We want to see whether or not something is increasing or decreasing. We want to be able to measure how much it's increasing or decreasing, finding the rate of change. Maybe we need to find if there even is a relationship between your variables. Is there a strong correlation? Is something happening? Maybe there's nothing happening. And then when we're communicating, when we're writing in a lab report, and you'll see this in journals, a good graph can communicate this well. Now, how do we do graphs well? Well, let's take a look at this. Well, we want to include a title, and it's a bit formulaic, but a good standby for us is going to be the effect of the independent variable on the dependent variable. A good example of this, and we're going to do this in about a month, the effect of pH on enzyme activity. pH is going to be our independent variable, enzyme activity, the dependent variable. So we have our title that shows that. Now the title could go above or the title could go below. For our purposes, it's probably better above. Now, what's a bad example of a title? I've had students just write enzyme graph, which doesn't really illustrate what you're doing. A good title will allow the reader to know what the graph is indicating. You should be able to have somebody look at your graph and go, oh, in this graph, I'm going to see how pH affected the enzyme activity. We're going to look at labeling axes. Now you want to label axes correctly, the independent variable on the x-axis, the dependent variable on the y-axis. You have to have those labeled. You can't leave those out. And if there are units, you need to include the units. Oftentimes these are represented in parentheses. pH doesn't really have a unit, but in our example, maybe you're measuring the height of a reaction. Well, then you want to put in centimeters or millimeters. Now, next we'll look at scaling. Now, this is oftentimes something that students get wrong. So let's make sure we go over this correctly. If we're looking at measuring something over different temperatures, and so we are communicating as the temperature increases, well, we want to show that increase. We want to indicate that our data is going from very, very cold to very, very hot. And notice in this graph, this scaling is showing it. So this is a good example. This would be very incorrect. So this is bad. And the reason it's bad is you're not showing that. You're not showing that the temperature is increasing. You're showing that it increases, then decreases some more, and then if you have another increasing, well, that's not going to show a good relationship. And then the other example of a bad one is if you're not showing good intervals. For instance, in this way that I've had students scale it before, they're showing the same distance even though the amount of spread is different. We go from 0 to 10, 10 to 22, and then 22 to 100, and that's not right. You're not going to get a good visible relationship. And then the last one, make sure your graph is visible. Good rule of thumb, between a quarter to a half of your lab pages. I don't want to see these real dinky little graphs that I can hardly read. You want a nice size graph. It doesn't have to take up the whole page, but a quarter to a half of your lab page. All right, so let's tackle this question about the right type of graph. We're going to be using line graphs, scatter plots, bar graphs, histograms, and pie charts. Now, pie charts are the easiest to explain. I can do this right now. There's no x or y axis. It's a circle. It compares parts of a whole, so it has to add up to 100%. So we can talk about that when we do the pie graphs. So before we get to the right types of graph, let's make sure we're clear about the types of data. Now, data can be called categorical, ordinal, or scalar. Categorical is probably the easiest one based on the name. It's categories. It's also called nominal. Think of names. That's where that comes from. Categorical would be no intrinsic order to the data. In other words, there's no increase or decrease. Gender might be a good one. So for instance, maybe you're measuring the weight of deer and you're wanting to compare male deer to female deer. Maybe you're looking at the differences in sexual characteristics. Well, it doesn't really matter whether or not the male deer or female deer are first. Color would be another good example. You know, if you're measuring the number of red-eye fruit flies versus white-eye fruit flies, it doesn't matter where they are. Ordinal would also be categorical, but it has an intrinsic order to it. Economic status, educational experience. We could make a graph that shows, yes, you have high school, you have a Bachelor of Arts, maybe you have then a Master's of Science, and then a PhD. Well, that has intrinsic order to it, even though it's still categorical. So you'd often see those represented in that order. And then scalar is the one that is probably the most familiar. You see numbers, continuous scale. That was our temperature example. We're seeing something going from very, very low to very, very high. There's actual numbers to it. So let's take a look at the types of graphs. The first one is a line graph. A lot of times we use these with data measured over time. Not always, but it's measured over time. The points may be connected, but this usually is if we're using the same individual or sample that's been measured continuously. If not, more likely a trend line is going to be used, and both of these graphs are seeing a trend line or a line of best fit. It's where we're looking at the data and seeing which line fits. Usually if you're going to eyeball it, you want the same number of points below as you do above. And you get better at this as you go on, but this data is really close. The other points are equally spread from the line. Quick word about line of best fit. They don't always have to have a linear relationship. A lot of students try to fit a line in there, but it could be a curve. You see the curve really nicely here, and then you see the curve flatlining there. So depending on your data, you might not want a linear relationship. Scatter plots are going to be similar to line graphs. So here's our second graph we're going to look at. They also use an independent and dependent variable. We use scatter plots to determine and show the relationship or correlation between two variables. Does variable A affect variable B? Is there a strong correlation between them? This is still scalar and it's still continuous data. Here's where we really want to look at a regression line or a line of best fit to determine the degree of certainty of the correlation. So there are measurements, and some of you have learned this in your math class. There are measurements to determine how closely these data points fit to a line. And we can use these formulas to determine that. Now, if there's a very strong correlation, for instance, over on the left here, we see a perfect positive correlation. Now, positive correlations mean that as one variable goes up, the other variable goes up as well. So in all three of these graphs, you see that as the x-axis is increasing, the y-axis is increasing. Now, what's different about them is how much they correlate. So we have a positive, perfect correlation. You could draw a line straight through those dots. A high correlation, the dots are relatively close to that line, and then a low positive correlation. And notice what's happening is the data points are spreading, and that's indicating a less confident set of data. And notice as the numbers going down, we see no correlation. These data points are all over the place. And then we get to a negative correlation. A negative means that as X is increasing, Y is decreasing. It's not a bad thing, so don't think of negative as being a bad thing, but it just simply means that as something goes up, the other thing's going down. And just as before, we can have a low, a high, or perfect. And again, that goes back to our confidence level about our data. So how about bar graphs and histograms? Well, bar graphs and histograms are very similar. Bar graphs use categories. Histograms use number ranges. You can see this nice comparison here. Bar graphs show gaps between the bars, and it's because they're categories. And then the histograms, they're touching because, again, we're showing that relationship as it goes up. These often are used to compare means of samples. You're going to see that throughout the class. And I just picked a real easy example. In Maryland, there's a park called there's an area called Soldier's Delight. It's a real fascinating one. And the trees are very, very different. The trees that grow there are very, very short. So we could measure the trees outside of Soldier's Delight, and we can get a set of maybe 5 trees. And then we could find our mean, our average, and then we could look at trees inside Soldier's Delight and get our average there. And once we have our mean, we can then graph that mean. Now, along with the mean, we also have error bars. And error bars are going to indicate how much our data vary. And in this example, they're showing that this is the mean, but this is the spread. The wider the error bar, the more spread the data had. Now over to the right is a histogram that's showing a fairly nice normal curve to it, where we have a fairly significant number of sample size in the middle, and then it thins out towards the end. You have examined this in your math classes before. So that we see with frequency histograms fairly often. Here's another example of our error bars. Notice this error bar is very narrow. That means there wasn't a lot of spread to the data. If you compare it to this error bar, that means whatever that category was had quite a number of widespread data. So even though notice these aren't too far different from each other, but this one is quite variable, this one is not. Well, there's going to be a couple of questions associated with these graphs, and then we have this one as well. And we're going to talk about these tomorrow and do some practice problems. Thank you very much.